Left off with the last video. I left my microphone at home, so I have to stay like close to my computer here, so I won't be up and down.
Good.
Shut up. The one thing I told the last class is that when we are looking at these transformations, and this is going to be something that if you start to understand this, and maybe you already have a good understanding of it because it's a lot of Algebra 2 was focused on this, is it's going to allow you to quickly and efficiently generate holistic graphs of new functions based off of what your parent function looked like. Does that make sense? So if you know what x squared looks like, there should not be a quadratic function that I give you that you cannot find the graph of and find the complete graph of, and quickly. Does that make sense? What I want to make sure we understand here real quick is an issue with generating graphs. Like if we have like g of x is equal to 2x. And you go back to what you did in Algebra 1, like the first time you ever graphed anything, you just chose x values. And maybe you got those 2 points and you plotted those, right? That's all you need, correct? Then you went to a new function. You went to, let's say, f of x equals x squared. And if we do the same thing, go 0, 0, and now I go like 416. Or even if you know that you need more than that, maybe you go 525. And you can keep, even if you think I need more points than that, you can go 749. You keep plotting those. Are you going to get a complete graph of the function by doing that? No, okay? In your first experience with x squared, maybe you didn't know that. But once you saw the graph, then you realize, oh, I need some things to the left of 0 as well. I need some negatives, right? Okay. Well, if I were to ask you to graph like f of x equals x minus 3 squared plus 12, and I asked you, make sure that you make the smallest table possible with choosing x values that are going to give you a complete graph here. So that you know you get a complete parabola here. Where do I start? Do I start at x being 0? Do I start at x being 1, negative 1? Because if I do that, those are still not going to be, if I use the same points I use here, or if I use my parent function points of like negative 2, negative 1, 0, 1, and 2 as my x values, I'm still not going to get a good graph. Does that make sense? But transformations allow that to happen quickly. It allows me to get that complete graph quickly. But when we do transformations, I want to make sure that we understand that there are 3 things happening, okay? 3 impacts of a transformation. There's an impact, if I start with x squared as my parent function, and I do a transformation to it, it's going to transform the way my rule looks. My rule looks like x squared plus 3 now. Does that make sense? It transformed the algebra, okay? It is also going to transform my table, okay, my set of ordered pairs. Okay, and we explained in the last video that this is only going to change the y values, right? Okay, increase the y values by 3. Kept the x values static, just increase them by 3. So it changes the rule, it changes the table, and it changes the graph, okay? I need you to think about all 3 of those things simultaneously when we're working with this stuff. Because if you just focus on what happens to the graph, you're going to get you're probably going to be successful with this, but you're going to miss out, okay? And things are going to get tougher than what they need to be if I just focus on what is happening to the graph. If I focus on just what's happening to the table, I'm going to miss out. If I focus on just what's happening to the rule and what that plus 3 means to the rule, I'm going to miss out. But if I understand all 3 of them together at once, it's going to be such a better understanding, and you're gonna be able to navigate this stuff so much easier. Okay, so as we do these examples with recognizing these next series of transformations, we're gonna do that. We're gonna look at all 3 approaches and how things change in all 3 approaches. Horizontal shifting is generally one of the harder transformations to analyze. Not to necessarily conduct and work with, but people get frustrated with which direction the graph is getting moved when we do a horizontal transformation, okay? It's called a horizontal shift or horizontal translation. But says we start with f of x as our rule, y equals f of x, okay? Then the way that we end up getting a horizontal shift is that we actually add c to our x value, okay, before we run it through our function, before we start to use the input procedure for a function in the evaluating process. Does that make sense? Okay. So you're going to transform your x before you evaluate. Okay, and that's what this notation here is saying. The notation, if we go back to a vertical shift looked like y equals f of x plus c, right? The only thing that's changed is that we've moved that right parenthesis out to include the c now, right? Okay, that little difference is going to now make sure that we move left and right instead of up and down, okay? I'm going to ignore this stuff. This stuff here is just kind of explaining the reasoning on why if I add c, it's actually going to move it left, okay? And if I subtract c, it's actually going to move it right. And I think we'll see that with the example that I want to work with here, okay? All right, so down here on this example, I'm going to start with my parent function, f of x. I'm just going to call it x squared. And I'm going to create a series of ordered pairs here. Now you would probably not, if you were doing this, you would not use this many ordered pairs. But to prove my point with these other two, I need at least this many. So if I had those and ran through my parent function, so negative 6 squared is 36. These should be easy for us to generate. And I told you in my previous video that these here are probably the 5 that you would maybe commit to memory. And it's I think, so trivial that it's really not even memory anymore. It's more instinct that you know those. You're never going to forget those. That's just knowledge now that you have possessed. You'll never lose. Those are the points that you would probably most traditionally use to work with x squared. But to prove my point with these graphs or these tables over here, I need a few more extra points. So here's the argument. If I look at g of x equals x plus 4 squared, and I choose the same x values, negative 6, negative 5, negative 4, negative 3, negative 2, what am I actually, so when I plug negative 6 in here, what am I actually squaring? Negative 2. Okay, and that's what I mean that when I ask you, when I tell you, are you doing something to x before you square? Are you doing something to x before you run through your order of operations, before you commit to the overall function? Does that make sense? The overall function here is squaring, correct? Okay, so we're doing something to x before we square. So I'm going to get negative 2 squared would be 4, right? Okay, if I plug negative 5 in, it's going to give me negative 1. I square that, I get 1, right? 0 is going to give me 0. Yeah, it's going to give me 1 squared, so 1, right? And we can, let's do one more. So we get 2, positive 2, go to 4, right? Okay. Well, let's look at this list of. So that list right there matches up with the other highlighted ones, right? Okay. How did I get those y values, though? How did those y values of 4, 1, 0, 1, 4, and these over here are 4, 1, 0, 1, 4, how did they construct themselves? Well, let's look at the x values that they were coming from. Look at that x value compared to that x value. Where is this x value in comparison to that one on the x-axis? They're 4 apart, which is that 4 right there, right? Okay. And it's to the left. Negative 6 is 4 to the left of negative 2, right? Okay. So that's the argument. That's the explanation up here that says when I subtract C, I'm moving to the right, and when I add C, I'm moving to the left. It's counterintuitive of what you would think. Most people think plus means move to the right, correct? But because it's getting done to the X first, it's actually a translation to the left. Okay, if I'm subtracting, it's to the right. So it's not any different over here when I do this one. So I go X and use H of X. And now if I go like negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. Now what I'm doing, I'm putting negative 8 through, so that's going to give me, 64? Just going to put negative 7 through. Negative 6. Negative 1. Gives me 1. It's going to give me 0. Okay. So now the repeat of these values starts to show up. Like, so looking at the 4, the 1, the 0, the next one's going to be 1, and the next one will be 4, right? But looking at those, how does that number right there that generated this first 4 in my list compare to that number right there that generated the first 4 in the list over here? It's 2 to the right. Okay. This one here is 2 to the right of that one. This one here is 2 to the right of that one. Okay. I think understanding the table there, understanding that something is happening to X before you square, reminds us that we're moving left and right. And it's counterintuitive to what you would normally think. If it's adding, you're moving left. And if you're subtracting, it's moving right. And hopefully this table expresses that. Working with GeoGebra here, if we take, I'm just going to start with f of x equaling x squared. Okay. The nice thing about GeoGebra allows me to take f of x and add c to it like that. Okay. If I've already defined what f of x was, now it's going to rename it as g of x when I do this, but that's fine. We just got to remember that this is f of x and this is f of x plus c. Is that okay with everybody? Mm-hmm. Okay. And what it allows me to do is take this red function, which was my parent function, and we'll just let that be static. We won't change that one. But it allows me to take this slider of c and allows me to move it left and right. And you can see what happens to the rule, and it lets you see what happens to the actual graph. So if I move it to the right, we see moving to the right, okay, so moving C to the right is what I'm talking about, which increased this to plus 1.8, right? But where did it move the graph? Left. Okay. Now what I want you guys to also look at, let's look at the point, how can I do this? If I look at 1, 1, okay, and that didn't do what I wanted. Okay, let's do it this way. X of A minus C comma 1. Okay. do you see how these ordered pairs of A and B, okay, the y value stayed the same, right? Because I didn't do anything to the y. I didn't add anything to the end of the function, like or a vertical shift, okay? I'm just messing with the c value in regards to the x, okay? How do these two numbers differ? These two x values here? By 3, right? So that's the same argument that we were looking at in the tables. If I look at that distance right there, you see that distance is 3 between corresponding points on these two graphs. That distance is 4. Now let's look at, it's rounding it. Let's go to 5. Okay, so that distance is 5. And you see that distance is then modeled inside these 2 points of the difference in the x's. Is that okay with everybody? Okay. Same thing happens if I move the other direction. Okay. And we see that difference in 5 in between those two x values. Does anybody have questions on shifting left and right? Now, it does not matter what your function is. So if I want to look at like the square root of x, does the same thing. Takes my parent function here of square root of x. If I want to move it left, I'm going to add something to it. And however much I add to it is that distance that it's going to move it left in. Okay? And what happens, I figured that would happen. Now I want to be able to make this always move. So let's go, I want a distance of, how do I do this? All right, so that distance right there of A to B is 3, right? Okay. Now, as I move A, is B still, no matter what, is B still 3 units away from A? Yeah, this. Yeah. So that's always the case as we do this, okay? So that's something I need you guys to kind of realize, and all that's doing right there is when I'm showing you these 2 points. Maybe I go down to, let's go up here to 1. So I got the 0.11 and the point -2,1. All that is doing right there, graphically, is showing you the same thing we saw in the tables over here, right? Okay. Does anybody have questions on that? So it doesn't matter the function, okay? So something that and this is why I want you guys to see this, and this is why I talked about a little bit in the previous videos. I showed you some like calculus concepts in the previous videos, because I want you to understand how important it is for upcoming tasks that we're going to have. Trigonometry is going to ask us to take something like y equals sine of x and y equals cosine of x. Okay, those two graphs. Does it look like one of them could be shifted to the right or left to get the other one? Yeah. Okay, so let's look at the cosine, which is this red one. I'm actually going to have to move it. So like 3, so let me put a line in here. X equals 3.14. Let's put pi in there, okay? Does it look like this point right there, where my cursor is halfway in between the y-axis and that line that I just put in there for pi? Yes. Okay, so that would be pi over 2, correct? Yes. Okay, so what I want to do, I'm going to take this red curve, and I'm going to move it to the right, pi over 2 units. Okay, so moving it to the right would actually mean subtract, right? And subtract from the x. And we see then that it shifted it or moved it pi over 2 units, and it became the same as the sine function, right? So there's going to be situations in this class, in trig, in calc, and really anything that you take beyond this, that those transformations are going to be prerequisites. Okay, it's going to be like, we're in this class, we can multiply now, right? I can assume that all this can multiply, right? So when you get into calculus, the assumption is everybody knows what transformations are, how they impact your graph, how they impact your table, and how you can use them to be efficient. Huh? Yes. All right, so I got a question for you. The next thing we're talking about is reflections. Okay, so we'll talk about these two reflections, and then that's all the further we got in the last class. So that's where we're stopped. So we talk about reflections, and this is something that you guys experienced with me in geometry. Okay. You guys remember talking about reflections, dilations. They were called translations. That's all the same stuff that we're doing now. Okay, that stuff was done for shapes, usually triangles. But what we learned there about the ordered pairs or the vertices of those shapes is exactly what's happening to the ordered pairs that we talk about on these functions. Okay, so back to geometry. If I would have given you this point right here, let's say it's just going off of the grid lines here, let's call that 3, 2, okay? If I want to reflect that across the x-axis, okay, we talked about in geometry when we do reflections, like if I just make this like a red piece of paper, and I say that I want you to fold this red piece of paper on the x-axis, is this point going to match up to some other part of that paper? What quadrant will that other part of the paper be? It'd be the fourth quadrant, right? So if I fold on the x-axis, this point here is going to match up to that point right there in the fourth quadrant, right? What's the coordinates for that ordered pair? 3, -2. We talked about in geometry that that's called an isometry. Okay? And our isometries were translations, left and right, and reflections. Okay? Those are what we called our isometries. Everything else, we could do we're not going to do rotations here with our functions. That's so that was geometry, but those are all called isometries. This is the same thing. And what isometry meant was that distance was preserved. It was a transformation in which distance was preserved, meaning that this distance here is going to be preserved down there. It's going to be unchanged, and then that distance there is going to be unchanged there. Okay, so that allowed us to come up with the rule that said if I have A, comma B, then this became A, comma, negative B. You remember that? Okay, we had some rule that looked like this. We said like capital R for reflection, and then we wrote a subscript like x-axis here, and we said A, comma B. That's going to give me then A, comma, negative B. That's what we talked about in geometry. So we expressed it there. Okay. Well, let's talk about this. If this is a function, isn't this going to be x and the y value be f of x if it's a function? Does that make sense? Well, then what would this point down here be? X comma opposite f of x. Okay, and if this is my ordered pair for a function, then the y value was determined by f of x. Okay, by the rule of f of x, whatever that was. Was it x squared? Might have been root x, might have been 2x, might have been whatever rule you want to come up with. So down here, the y would have been written as the opposite of f of x. Does that make sense? So the idea here, and the reason I displaying it this way, is that when they're gonna like use notation that seems sometimes cryptic on what am I supposed to be doing? Because I think it's easy for people to say, well, if my rule is 2x, if that's my function, then y equals negative 2x. Oh, yeah, that's a reflection across the x-axis. I see that negative out in front. But a lot of times they don't use 2x. A lot of times they don't use x squared. They use the collective generic f of x to express that it doesn't matter what your function is. Does that make sense? Could be sine of x, could be logarithmic, could be exponential, could be, could be tangent, could be whatever. Okay, it doesn't matter what your function is. So they use the generic term that stands in for all of them. Okay, so our rule says, come over here. So to graph y equals the opposite of f of x, you reflect the graph of y equals f of x in the x-axis. Okay, so if we've got, let's just do this example A down here with the table real quick. If f of x was x squared, okay, we would have, going off of our parent function, we have 4, 1, 0, 1, 4. We'd have those ordered pairs, right? Okay. Now, if I wanted f of x to be the opposite of x squared, well, I'm going to have negative 2, negative 1, 0, negative 1, negative 2. And the rule says if it's a negative out in front like this, the only thing that changes is the y value gets negated. Does that make sense? So I take my original function and my y values get negated. And now those are the ordered pairs over here for the opposite of x squared. Is that okay with everybody? Okay. So if you remember, it would have been the first video that I talked about this. Oh, I didn't say it here. All right, let me see. All right, so you remember seeing this handout? Okay, and I told you, obviously there's some of these on here that you're not going to commit things to memory, like x, 1, 1, 2, 2, 3, 3, those are ingrained in you. Hopefully same thing with absolute value, hopefully the same thing with square root. But if I'm doing a cubic, okay, so I want some parent function points, like 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. And if I know those, then when I do a transformation, I ask what's the opposite of x cubed? Then all you gotta do is take those y values of those 5 points I just memorized and just negate them. And now I've got the y values for negative x cubed. Does that make sense? Okay. Same thing for like square root. Okay, so if I have square root and I want to know, okay, so the key points on here are, let me get a tool here to draw. All right, so if I have 0, 0 here, and I have 1, 1, I have 4, 2, and I want to come up with what does f of x equal the opposite of root x look like. What do I have to do with those y values? Just make them negative, right? So 0, 0 obviously stays 0, 0, but 1, 1 becomes 1, negative 1. 4, 2 becomes 4, negative 2. And now we just got the complete graph. Okay, I got the complete graph, and I really didn't have to do much work, right? I didn't have to do any evaluate or anything like that. I know the relationships between the rule and what that's going to do then to my ordered pairs. And then I can graph that. Does that make sense? Okay, so here's my question. We are going to go back to this here. So now instead of looking at the opposite of f of x, let's look at f of the opposite of x. So there I'm negating the x before I run it through the function. Does that make sense? Okay. So if I'm in GeoGebra here, I'm just going to create just some random function. So let's say if, let's go between 1 and 7, then polyfit A, B, C, D, E. Oh, wrote that backwards. There we go. All right, so I get that function. Okay, so that is the function f of x right here. Is everybody okay with that? Okay, I'm going to write a new function. I'm going to say g of x equals, okay, so I just have to label it as a new function. So don't worry about the g of x, but I'm going to put a negative out in front and then type in f of x. And you see that that gave me that x-axis reflection. It gave this gray line here, a gray curve, right? And it's basically folding on the x-axis and seeing what is generated, right? So that's just changing the y values. Is everybody okay with that? If I were to look at, let's go perpendicular line here and look at the intersect between those two and those two. So I look at these 2 points of h and I right here, which are the intersections of this black line and those two curves. Is that okay with everybody? See h and I there? I know it's kind of zoomed out, but what's the only difference between these ordered pairs? Y value is negative. Okay? Let's do it this way. Instead of looking at multiplying the entire function by a negative, like I did here, let's get rid of this, and let's say that g is now the f function, but wherever you saw x, you're going to make x negative. What line did it reflect it across? The y-axis. Okay. The idea then is, so if I look at, let's see here. If I go look at the point x, how am I going to do this? Let's do it this way. Parallel line to there. And let's look at the intersection then of those and the intersection of those. I know it's a lot of points, but I want to look at K. Let's look at L and M. L and M. If I look at L and M, okay, these 2 points, L and M, what do you notice about their ordered pairs? Only the x is negative, right? The x's are opposite, okay? And that's going to be the same no matter where I take this line and move it, is L and M, or the x is always opposite. Are K and N, are those opposite? Okay? That's a hard concept for a lot of people working with it's called a horizontal reflection because the graph moved in a horizontal orientation. But if I've got, let's just say y equals, give me a function. X cubed. Okay, so if I got x cubed, okay, and then I look at y equals the opposite of x cubed, okay, those are going to be a y-axis reflection across from one another. So if I look at y equals x cubed, 0, 0, 1, 1, and 2, 8 are going to be key points on that. Okay, so that is my curve for y equals x cubed. Is that okay with everybody? Okay. This, all it means, okay, if I understand the relationship between these two and where that negative is now it means it is a y-axis reflection. So this point of 1, 1 is now negative 1, 1. Does that make sense? This one here of 2, 8, negative 2, 8. Here at negative 1 becomes 1, negative 1. And -2, -8 becomes 2, -8. And we get that. That make sense? I should go through 0, 0, but. Does that make sense? Okay. Now, did I have to create a table or anything like that? No. Okay. Real quick question. If I gave you something like, gave you f of x equals x squared, okay, and then I asked you graph g of x, which is going to be, let's go f of x plus c minus d, something like that, create these sliders. And I asked you to find the ordered pairs that are going to give you this purple graph, okay? So maybe I hide that from you. I don't even give you that. And I asked you graph this thing, okay? Before you ever learned anything about transformations, the only way that you could have done that is you start choosing x values of like 0, 1, 2, 3, 4, 5, 6, and you evaluate them, right? Okay? But now I don't need to do that because now don't you know a point on x squared? Give me a point on x squared. 0, 0. So you know 0, 0 is on x squared, right? So then on the purple graph should be 0. What does this negative 2.9 do to my x? Moves it to the right. So I'm going to add 2.9 to that. Okay? And then I started with a y value of 0 on the parent function. And what's this negative 2.7 going to do? Move it down. And it goes from a point that's on the parent function to a point that's on the family graph, okay? Or you might want to call it like a child's graph. Does that make sense? Like parent, child, okay? What if I go 1, 1? 1, 1's on there, right? Now, to get that corresponding point on the purple one, it'd be 1 plus 2.9, comma, 1 minus 2.7. They correspond, right? Is that all right with everybody? Can we do that? Okay. So those are your vertical transformations, horizontal transformations, and reflections. Tomorrow we'll talk about vertical stretching, okay, and shrinking. And I'll introduce you to horizontal stretching and shrinking. But horizontal stretching and shrinking with our polynomial functions, our rational functions, our logarithmic functions, they look like vertical shrinks and vertical stretches. So it won't be until we get to trig, and we'll talk about things called periodic functions, that we can actually see a horizontal stretch. So that'll be tomorrow. Nothing new in regards to homework. We are getting close to wrapping this unit up, this chapter up. Okay, so probably mid to late next week. Next week we don't have school on Friday, right? 30th? Huh? So I'm thinking probably next Thursday, Wednesday, having a test over these first 2 units. Okay? And I will give you probably later this week a practice test to kind of refine your skills with that stuff.